Okay, so welcome back. This is part 4 in our series where we show you how to convert your Arduino into an oscilloscope. And you can see this application here where we're feeding from our function generator into the oscilloscope, these two wires down here. And it's basically a 100 hertz sine wave coming into our Arduino, and we're plotting that in this application on our Windows 10 computer. And it's basically an oscilloscope, and it's got triggering, and it's got making measurements of average and max volts and frequency, and we can adjust the time scan and a bunch of stuff. So we're going to show you in this video, in this part 4, we're going to talk about some very important tools and techniques that I think are very important if you're going to be designing a project such as this. And honestly, I use these tools and techniques in just about every engineering project I do. Because if you're going to design something like this that can get kind of complicated, and we're going to have timing issues and different limitations, such as Arduino limitations, you're really going to have to understand each step of the process if you want to make sure you're getting good results. So in the previous videos, we talked about the design phase where we came up with this block diagram. And what we're going to focus on in this video is some of the tools and techniques to make sure that each block of this diagram, not only do we understand what's going on, but we make sure that we have good data coming in and good data going out for each step of the process, because when we finally get our results plotted on the screen, we're going to want to make sure that it's accurate. And if we have some bugs, if we get a blank screen, we're going to have to know where in the process we should look to find out what's going on and what's not correct. So these techniques are going to be very useful to figure out and understand the process and the inputs and the processing and the outputs for each block. Now there's an old engineering expression which is garbage in, garbage out. So for each block of the process, if you put garbage numbers in, you're going to get garbage out. The goal here is to make sure you don't have garbage in and you don't have garbage out. You need to understand what's going in and what's coming out and what the processing is doing. So to do that, we're going to use a couple of tools that, again, I use many times in many projects, and we're going to discuss how you use those and how you can implement them. Now, if you like any of these videos, I've got about 180 videos in this channel over the last 5 years. If you like any of them, I encourage you to hit the like button and subscribe and hit the bell notifications. And most of all, please let others know that we're here so we can get some more viewers. Honestly, I get like 50 views for many of my videos, and it's kind of depressing if over a couple months I only get 50 views. So if you like any of these videos and you want them to continue, please let others know. So the first tool I want to talk about is something I have a lot of videos discussing, and that is Microsoft Excel or any other spreadsheet application. So why is that important? Well, if you look at our oscilloscope application, for example, you can see that I'm doing a frequency measurement. I'm measuring the frequency of these waveforms each scan. And again, I'm updating over here about every 230 milliseconds. So 4 or 5 times a second I'm updating this. And each scan I'm measuring frequency. And you might notice that the frequency is bouncing around, give or take 1 hertz out of 100. If you're going to design something like this, it's really good to know in the beginning what you should expect for accuracy of your measurements. So what I did early on is I put together a spreadsheet to figure out what I should expect for accuracy of frequency measurements with this oscilloscope application. Now, if you think about it, depending on how often you sample your input waveform, in this case 100 hertz waveform, the sampling rate determines how accurate your frequency measurements are going to be. I'm simulating what I can expect for frequency accuracy based on 500 samples per scan, and I've got 100 millisecond scan time like I've got here, and I'm feeding it 100 hertz waveform. So based on the scan time and how long it takes to do the scans, there's going to be a time between scans which is going to result in an inaccuracy. And this basically tells me I should only expect an accuracy of plus or minus 2 hertz. And you can see the results are it's actually, 1 hertz accuracy. And that's because I've done a little bit more magic in my code to make it a little bit more accurate. So it's those kind of things you need to be aware of, because if you're going to get results like this, you may think, hey, something's wrong. No, the only thing that's wrong is that you have a very limited scan rate. Another thing I used it for is to calculate what I call the 10-cycle frequency. Now, what's a 10-cycle frequency? Well, if you look on here, if you're going to have an oscilloscope, it's nice to make sure that you can see your waveform, and you want to make sure that you're going to be able to see something around 10 cycles of your waveform. So here I've got 2, 4, 6, 8, 10 cycles. That's nice because I can see 10 cycles of waveform. If there's a lot more waveform crammed in here, I'm not going to be able to see the individual cycles. So I want to make sure, based on the samples and the scan time, what kind of frequency am I going to see 10 cycles of? So I use this Excel spreadsheet to calculate, to say if I've got 2,000 samples, I can only see 10 cycles of a 250 hertz waveform. Anything more, anything higher frequency, I'm going to see more than 10 cycles, okay? So if I want to see like 10 kilohertz down here, I can only have 50 samples per scan. Now, another thing you can do in Excel or a spreadsheet application is, if you're going to get down in your application down to the binary and hex numbers, there is some functionality in Excel where you can convert between decimal, binary, and hex. And for example, there is, if I want to take a decimal 2 and convert that to binary, there is a DEC to BIN function where I can calculate directly what the binary version of a decimal number, and same thing for hexadecimal, BIN to hex. And there's a bunch of other binary and hexadecimal functions that you can use. Now, another tool I want to talk about is something I use all the time, and I've got a lot of videos talking about it, and that is LTSpice, which is a simulator software for electronics and electrical circuits, which is extremely, extremely valuable and useful if you want to learn how stuff works. So why would we need LTSpice in an Arduino project? Well, if you look at the Arduino in this block diagram, the main functionality in the Arduino is this analog to digital converter, which takes the 0 to 5 volts in and converts it to a value from 0 to 1023. And you can simulate an analog to digital converter in LTSpice if you want to learn how the things work and what to expect. So, for example, here is a circuit that is kind of a example circuit that you can get for a Linear Technologies analog to digital converter. And all you have to do is go up here to the components, and up here you can see ADC. One of the sets of components that are available is an analog to digital converter. And you click on that, it's got a bunch of different analog to digital converter circuits. So you can select one, and you can see, open this macro models example circuit, which will give you this example circuit to show you how it can be hooked up. And then you can use that to simulate an analog to digital converter and see what you can expect. So very, very, very useful. We may even do a video later on about analog to digital converters in LTSpice, but really great way to learn how they work. Now, another practice that I think is extremely useful is making sure that you not only document your code when you're writing software, but make sure that you define in each step of the process what the expected inputs are and what the expected outputs are. So for example, in the CSharp code that we're going to be developing, here is where I'm reading the burst of data from the Arduino, and I'm writing that in the documentation, we expect at this part of the process, when I've just read the code, each sample is going to look like a string that has this value and a carriage return and line feed character. So I know exactly what the string is going to be coming in from the Arduino. So I know that, oh yeah, it's got a carriage return and line feed. I need to get rid of that. So very, very important that for each step of the process, you know exactly what to expect so you don't miss anything and you don't end up getting, like we said, garbage in, garbage out. Now, one other area that is extremely, extremely important, especially with an application like this that can get a bit complicated, especially when we're dealing with timing issues, it's very, very important to get feedback on what the actual numbers are. Right? A lot of people like to just kind of wave their hands and assume that things are going okay, but it's so much more helpful if you actually look at the numbers for each step of the process. And in this case, we're going to have to look at timing numbers to make sure we've got the correct timing, as we talked about in the design phase. So what I like to do with my applications, and we've done here, is set up a separate debug mode. And you can see I've got a little checkbox. And you can imagine if the checkbox is checked, there is some code in my application, in this case CSharp, that says if this checkbox is checked, then output some data to this text box that gives us, in this case, timing data. So I'm going to check this, and you can see that suddenly we change what's displayed in the text box with actual timing data. And this data is how much time it takes to do a scan, and we can see that we're every 230 milliseconds we're updating or refreshing the scan, and it's giving us the actual times so that we make sure we're not having any problems. So with the debug mode on, I know that the total time to send a request to the Arduino to get data, return that data, process the data, and plot it is 180 milliseconds. You can see the first number here. So I have a function in C# called a stopwatch that is measuring the actual time it takes to do that, and it's outputting that data. Now I've also included a safety buffer, which is the second number, total buffer time. I've included a fixed 50 milliseconds for each scan to make sure we have time between scans and we don't step on toes and make a request before everything's done. So the total interval, the timer interval that's updating this, is now about 230 milliseconds. So all I need is this one checkbox, and I'm doing a very simple print to this text box. And this is only like one line of code to get this data printed to the text box. And we'll go through that in a bit. But you can see it's very, very important you get the actual numbers. Don't just assume, don't just wave your hands and make believe you know what's going on. Look at the actual numbers. We're going to see how it's very, very simple to do this, but you have to keep it in your mind. Don't always be just chasing, getting an answer and assuming it's okay. You have to look at each step of the process as an engineer would and evaluate to make sure you got the correct data in each step of the process. So let's take a look at some of the tools in C# or whatever application you're writing this in, what tools we can use to do this debugging to get some really good feedback so we can know each step of the process what the actual numbers are. So here we are in our C# application, and this bit of code is the code that gets executed every time the system timer sends a request to the Arduino to get a burst of data. And you can see here, this line, Arduino port, we're sending a command to the Arduino with a B and a number of milliseconds of bursts to acquire. So we're sending the request. And right here I am starting or restarting a stopwatch, a C# stopwatch. At the point that I send the request, I am starting the timer, and I am then executing this function that goes out, grabs the data from the Arduino over the USB port, processes it and plots it, and then when that's all done, I stop the stopwatch, and here I calculate the elapsed time. So all I've got is 3 lines of code, and I can get feedback on how long it actually took to go out, grab the data, process it, and plot it. And I have now put that into a variable called burst time, And down here, I can just send that value to the text box. So really, it doesn't take a lot of code or effort to do that. And it's a really good mindset to get into, especially if you're doing timing related applications, where you can very simply find out the elapsed time to do something, send it to a text box, and you've got the data. So really very simple and really a great thing to keep in mind for doing debugging. So I've got another feature here where I can do a single shot. I can take a snapshot of the waveform and save that to a CSV file. So all of the data for that scan gets saved in a time, value CSV file. And all it takes is this one line of code. I've got my array of data with times and values, and all it takes is one line of code that says file.write all lines in that array, and it specifies the path of the file name, a CSV file, and sends that array to the file. So really very nice, because once I've got that CSV file of all the times and values of that scan or that burst of data, then I can take that into Excel and I can analyze it, or I can bring it into LTSpice and use it as a source, and I can analyze that. Very, very useful thing to use CSV files. I use them all the time. And if you keep that in mind, that you always have that very simple one line of code that you can grab data into a CSV file and analyze it, it's really, really very useful. And of course, if you are using an Arduino in your project, it is extremely important that you get familiar with and use the serial monitor. Control-Shift-M. When you have your Arduino sketch written, you can start up the serial monitor and you can monitor what it's sending over the COM port when it does a serial.println. And you can also send a command up here in the top right. You can type in a command and send it to the Arduino and see how it responds. So very, very useful to see what the Arduino is doing and how it's responding to commands. And of course, you've also got the serial plotter, which can plot the data coming from the Arduino. You can plot the values coming from the Arduino so you can see if it's as you expected. So now the last thing I want to discuss is something that I encourage you not to do. If you're writing applications, a lot of people on the internet will advise you to find a library and download the library to do what you need. And while sometimes that's unavoidable, you have to, keep in mind that often that is probably not your best choice. And I say that for a bunch of reasons. Personally, I avoid at all costs, if it's at all possible, I avoid using other people's code if I can possibly do it myself. What that requires is you understand what the code is doing and you do it yourself. A lot of people like to, they like open source free software because it's free and they can just download it and act like they know what's going on when they don't have any clue. I like to actually understand stuff. So we found in a previous video where we developed a frequency monitor application, and we looked at a freely available open source library that a lot of people are using. And we found that the code was not only incorrect and we had to fix it, but it was also a lot more than we needed. And we only needed like 5 lines of code, because if you understand it, a lot of times you don't need all the code that's in the library. And you can save yourself a lot of headache, because if you're using somebody else's library, it can be very, very difficult to debug it because you don't know what's going on. If you can distill it down to like 5 lines of code that you understand and you develop yourself, it's so much easier to debug. I just encourage you to be very wary of using other people's code. Even if it's free, even if it's open source, doesn't mean that it's good and that it's something that you need and that's good for you. It also removes an opportunity for you to learn about stuff. And in the engineering world, you need to understand stuff. You don't provide any benefit by just copying and pasting code. You need to understand stuff, because that's how you deal with things going wrong and you fix problems you understand them. So again, I encourage you, if you have an opportunity to download a library or somebody else's code, think twice and figure out what's actually going on, what you actually need, and see if you can do it yourself. It could be very beneficial. Anyway, I encourage you to hang around for the future videos in this series where we get into more detail on how to develop this application. Again, if you like any of the videos in this channel, please hit the like button, subscribe, hit the bell notifications, and most of all, let others know that we're here. Otherwise, take care. Have a really good day. Thanks.